The large effort undertaken by NASA, ESA, and other space agencies toward lunar exploration calls for an adequate navigation and position infrastructure. ESA's answer to this need is the Moonlight Initiative, which aims at the development of a reliable yet simple lunar communication and navigation service. Our paper presents a novel concept for orbit determination and time synchronization of such a system. The proposed approach is based on small ground antennas that simultaneously track the entire constellation using two-way microwave links, implementing the concept of multiple spacecraft per aperture, MSPA in short. The proximity of the Moon and the need to minimize the supporting ground infrastructure makes MSPA a very attractive solution. In MSPA, multiple radio links are established from a single ground antenna using a unique code for each satellite. In order to track simultaneously the entire constellation, the size of the ground antenna must be small. For the orbital parameters considered in the ESA Moonlight project, ground antennas of just 30 centimeters in diameter must be used if the link is in K-band. At X-band, the maximum diameter is about 1 meter. Antennas of this size can be easily deployed at multiple sites, making a coverage around the clock quite easy to implement. In spite of the small diameter of the antennas, we show that the proposed MSPA architecture enables sufficient data rates to control the constellation, including the upload of the navigation message as frequently as needed. In addition, MSPA provides high accuracy in the traditional Doppler and range measurements, enable a very precise orbit determination. Another advantage of MSPA is the straightforward generation of single-beam interferometry observables, providing differential range between any pair of satellites of the constellation with a precision of 0.1 millimeter or less. We assess the achieved time transfer accuracies, both using the standard asynchronous two-way satellite time and frequency transfer and a time transfer method which leverages on onboard code epoch timestamping and precise spatial range information. Finally, we propose also an efficient structure for the navigation message and discuss the reference frame and associated timescale for user positioning in a relativistic context. We complete the analysis by estimating the attainable accuracies in the signaling space error.